Ashwin, do you have any doubts so far regarding the course? Do you have any specific questions regarding this sessions?
Yes, sir. Regarding, I've gone through the weekly courses, but a few of the courses I was not able to complete.
Okay.
I'm a student from electrical and electronics background.
Okay.
So the main intention of choosing this course is to switch to an aerospace field.
Okay.
So I'm preferring to take a master's also in aerospace, especially dynamics and control, which is allotted in IISc or in IIT Madras.
Okay. Nice.
Uh, uh, so what are the basics that I need? I found difficulties in like vector fields and mechanical related problems. So how do
Vector
I
fields.
overcome that?
Okay, vector fields, it is common in electricals also, right? I believe you will
Mhm.
also get same kind of mathematical things if you're your bachelor's right now. So which year you are in?
2014 actually.
Sorry,
2014.
your bachelor's you are done 2014,
Yes, yes.
and
I'm
now
a
you are
working
working,
professional.
okay, working professional, nice.
Yeah.
So I think then you might have encountered all these vector fields and divergence, like how to handle the scalars, vector calculus
Mm,
basically, if I say.
yes.
Yes, okay. If you are familiar with the vector calculus, these things are easier for you. But to get more understanding of this aerodynamics, I
Hmm.
suggest you to read or take the course of fluid mechanics also, so that it will get more insights. You will get more insights of what we are actually doing in this aerodynamics. In
Okay.
any aerospace student or any particular student, they will first undergo to the course of the fluid mechanics,
Hmm.
and
Okay.
then they will start the aerodynamics. So it will be easier for him or
Okay.
her,
Okay.
whatever it is.
Okay.
Okay. So this also you can try some concepts,
Hmm.
whatever you're not able to understand, you can specifically ask that particular concept. This is one that you are unable to understand. I will help you to in this through this online sessions.
Sure, sir. Sure.
This is meant for that, specifically for to interact with the learners. So if you
Hmm.
have any specific comments also, you can share your screen and you can ask me. I will try to clear.
Okay.
Okay. And anyone having any specific questions before starting the session? Tanmay,
Sir, actually, I had a question about velocity potential.
velocity potential. Okay.
So,
What is
sir,
your question?
there was a question in the assignment, if I'm not mistaken.
Okay.
Let me see the question.
Devi Pratap Singh, you have any specific questions in the meantime regarding the course or any doubts in the assignment? Only doubts, not. Wait.
Yes, sir. It was question number 11 in the assignment 3.
Assignment 3. Okay, you are talking about the recent assignments.
Yes, sir.
Recent assignments I haven't looked yet. Let me see. Like, can you share your screen and explain where you are, like, if you are doing something solution and you stuck somewhere? I can help you with that. Do you have solution something on your screen or any photo kind of thing?
Okay, yeah, just a minute. So there's no option for screen sharing.
Okay, let me open the course then. So week 3, right? You are telling?
Yes, sir.
Week 3 assignment, week 3. Okay. Question number?
11.
Okay. Consider the flow field given by V bar equals to some vector velocity field, that one. Here T is in second. That is the question you have?
Yes, sir.
Okay. So what is the problem in solving this?
Sir, I don't know how to find velocity potential, or I don't know what velocity potential is. I don't think it was covered in the course.
If I'm not wrong, I'm going to cover this today. Yeah,
Okay,
I
sir.
will cover this in this today's session.
Yes, sir.
You are okay? I will cover it in these 2 hours. If not, if it is not covered, like if the time is not sufficient, I will end 5 minutes I will take at the end and I will tell you.
Thank you, sir.
Okay. So let's start our today's session. I hope you are all able to see my screen. Kindly take the notes, some important equations also you will get, and let's start. Okay. So last time we stopped it here. This question is question 9 from last week. We have 2 more questions, question 9 and question 10. So to understand this question, I will just give you the basic of overall understanding of the question. What is this happening here? The question is asking us, suppose you have a particle at, let me take my cursor. Okay. Suppose you have a particle like this, assume any particle in the atmosphere that is showing like this, and it is having a density ρ1 dash, p1 dash, and some temperature T1 dash, and it displaced from the height h1 to height h2. After displacing, it acquired the properties like ρ2 dash, p2 dash, T2 dash. Okay, so at height h1, the surrounding temperatures of surrounding properties of this of these particles are ρ1, p1, and T1. Okay, and after displacing, it attains some height, that is h2, and there the density in the atmosphere ρ2, p2, and T2. And the question is like whether this particle will come down. I mean, after reaching h2, will it come down to h1, or will it retain its own same position where like h2 will it retain there itself, or will it go still forward, like will still up towards the height of the toward the height? So, or it will stay at the same position. This is the question they are asking, and they gave some more information about the atmosphere laws, like atmosphere is obeying P equals to K rho to the power N, and N equals to 1.235, this law, pressure and density relation, with N equals to 1.235, and you have N equals to 1.0. These are for troposphere and stratosphere, these N values. So now our task is to identify this, like these 3 questions, like whatever, whether it stays at h2, whether it will come down, whether it is, which one will happen, whether it is continuously goes up. These 3 are referring as simply as stable, neutrally, unstable. That means if particle is going from h1 to h2 and again it retains to h1 position, like a ball, if it is moving up and it is again coming back to h1 position, then it is a stable particle. Then if it is going to h2 and remains there, then it is called a neutrally stable particle. If it is continuously going up, then it will called unstable particle. So this is what we discussed last time. And other important things also, like adiabatic process. Adiabatic process means, suppose if any particle is there h1 and it is going to h2, there it is doing some work, and during this work or during this displacement, if it is releasing some heat from its boundaries, then that process we call non-adiabatic process. If it is not releasing any heat, that is Q equals to 0, Q represents the heat transfer. If Q equals to 0, then it is called adiabatic process. So no heat transfer to the surroundings. Then we call that particular index N will becomes equals to gamma, where that, see the relation, if there is no heat transfer, then the relation N equals to the P and density relation will be like this, where N becomes gamma. Gamma is the constant, that is the ratio of specific heats we call, that is 1.4. Okay, these are all some insights and important aspects that you need to remember while solving this problem. Okay, then the next question is density of the particle. Not next question, it's a concept that you need to understand, whether the particle, how, like, to define the answer, to choose the correct option in 1 2 3. First most important thing is that you need to understand the density ratio of the particles at different heights. So let me clear the things and we can discuss it further. Okay, it's stuck. Let's go to the next slide. Okay. Pen, fine. So now I have a particle here, and this is height h1 and this is height h2, and suppose this is density rho2 and this is density rho1. Your particle has the density of rho1 dash and here as the rho2 dash. Now to decide whether the particle, how the particle will react at this particular position, means it purely depends on the buoyancy at that particular location, that is h2. Suppose if my density of this particle rho2 dash is greater than rho2, that means surrounding density, and it is particle density. If particle density is greater than surrounding density, then your particle will come down, because it is from the class 6 or class 7, you can easily understand the density differences is there. The movement of particle will automatically appear because of the buoyancy forces. So if your rho2 dash is higher than the surroundings surroundings density, then it will come down. Then it is called as stable mode. That means what should happen? My rho2 dash by rho should be, rho2 dash by, this should be greater than 1. Okay, and the same thing, if rho2 dash by rho2 equals to 1, then it will be neutrally stable. Why it is neutrally stable? Because my density at rho2 dash and rho2, I mean this particle density and the surrounding density are both same, then it is neutrally stable. And the third one is rho2 dash by rho2 is less than 1, then it will continuously goes up. That will called as unstable particle. Unstable particle. So these are our three conditions. Now your task is to understand how you will get this rho2 dash by rho2. This is your primary task. What we have is, we have a relation of pressure to density, that is pressure equals to K rho to the power n. But how will you connect this pressure and density with the particle, that is rho2 dash and rho2? This is your important aspect that you need to understand how I can connect it. So by using the perfect gas equation, that is P equals to rho RT. Okay, if your P equals to rho RT, I can write it as P2 equals to rho2 RT2 and P2 dash equals to rho2 dash RT2 dash. This is for surrounding temperatures, surrounding atmosphere relations, and this is for the particle. Now you separate your density. How to separate that? P2 by P2 dash times T2 dash by T2 equals to rho 2 by rho 2 dash. What we need? We need, sorry, let me write here. Okay, I will write here. So now your rho 2 dash by rho 2 equals to P2 dash by P2 times T2 by T2 dash. This is your equation. So now what we can do? If you see carefully, I need to tell you some further insights like how the pressure and temperature varies when you are going up. If you are going up and suppose if the particle is at H1 and it is, sorry, suppose your particle is H1 and suppose it is the particle of that H1's atmosphere only at initial time T0, then your P1 dash particle pressure equals to surrounding atmosphere pressure, rho 1 dash equals to surrounding atmosphere density, and T1 dash equals to surrounding atmosphere temperature. At the same way, if any particle is moving from H1 to H2, then it will acquire, it will expand or it will compress to that particular pressure at that height. That means your P2 dash equals to P2. Okay, so that is how your pressure or any particle, if any particle is expanding to or moving to some particular location at height up or down, it will acquire the pressure of the surrounding temperature. So that means P2 dash equals to P2. Then what will happen here? Our rho 2 dash by rho 2 equals to T2 by T2 dash. So now how we can write this T2 by T2 dash? Let me write further understanding, further expansion. I will write, we need to get T2 by T2 dash to get rho 2 dash by rho 2. I will just write, suppose, let's say how to find out T2 dash by T2, which I can expand it like T2 dash by T1 dash, T1 dash by T1 and T1 by T2. Now you see, if you cancel out T1 dash, T1 dash, this one will cancel out, T1 will cancel out, and you get T2 dash by T2. It is just a chain rule kind of thing. So this is your important relation. You need to write like that. This will give you the relation between height H1 and H2. So we included the H1 parameters and H2 parameters between two, and we combine many things here. So in this way, you will get, because your T1 dash equals to T1, see this here, your T1 dash equals to T1, you will get T2 dash by T1 dash times T1 by T2. This is what you will get. Okay, now we have some understanding that rho 2 dash by rho 2 equals to, you just reverse it, T1 dash T2 by, and this is T2 dash by T1. This is what our equation. So let's find out these two, how to get these two. T2 dash by T1 dash, T1 by T2, and if we substitute these two in this equation, the right side density equation, we can get an understanding of how this particle will behave. But how to get the relation between temperature to the density or temperature to some other parameter? Now we don't have direct relation because we don't know the temperatures ratio, or we just only have the variables, but we need to understand in some other way how the density is varying. So for that purpose, what I will do is I will generate a relation between temperature and the pressures. because we know the pressures are same. P1 is equals to P1 dash and P2 is equals to P2 dash as this one and this one. So it will be much easier to understand since these are all known parameters, like compared to the density and temperature, pressure you have known. So it is much easier if I can convert the temperature relations to pressure relations, so I can easily cancel out the things. So let's say how can you transfer? Suppose you have a particle like this. Again, let's consider the P1 equals to rho1 RT1 between two heights, that is P2 equals to rho2 RT2. You have a relation like this. If you simplify this, you will get T2 by T1 equals to P2 by P1 times rho1 by rho2. Now we also have P equals to K rho to the power n. That means if you take out the constant to the, if you simplify, if you rearrange this algebra, we can write as P1 by P2 whole to the power 1 by n equals to rho1 by rho2. Fine. Then let's substitute this P1 by P2 or rho1 by rho2 in this equation. If you substitute that, what you will get? You will get T2 by T1 equals to P2 by P1 times P1 by P2 whole to the power 1 by n. This is what you will get because you just substituted that rho1 by rho2 in this form. And then your final equation, if you simplify this algebra, it is P2 by P1 whole to the power n minus 1 by n. This you should keep in your mind. If you are familiar with the thermodynamics, this we called as polynomial form. Let me where is the options? Okay. Yes. Called it as a polynomial process. That means n can be depends on the state, whether it is heat transfer or not, work transfer or not. So there are some options. So n minus 1 by n. So this is the important relation of your temperature and pressure. So now just substitute this equation back to your this one. That means you need to replace the variables accordingly to it. So how do you replace it? Now first one is let's say T1 dash by T2 dash, right? T1 dash by T2 dash, or let's substitute directly because we have this format T2 by T1. These are all same. Let's substitute in this T2 dash by T1 like this format. What you will get? You will get T2 dash by T1 dash equals to P1 dash by P2 dash whole to the power say n minus 1 by n. And in the same way, if you substitute for T1 and T2, you will get T1 by T2 equals to P2 by P1 n minus 1 by n. These two are the required relations. Suppose you have to understand one more key concept, that this is your particle one and this is your surroundings temperature ratio, this is your particle temperature ratio. Since your particle temperature ratios P1 dash, P2 dash, the dash represents the surroundings and particles. Very carefully if you see, P2 dash equals to P2, that we already seen here, P2 dash equals to P2 and P1 dash equals to P1. Okay, now let's consider one important assumption here. Since the particle is moving quickly, assume the particle is moving very quickly from H1 to, this is your H1 to H2 very quickly, it does not have time to release the heat or acquire the heat from the atmosphere. That means Q dot heat transfer rate is equals to, or net heat transfer is equals to, sorry, net heat is equals to 0, not even, it's not. There it is. Yes. This is equals to 0. Fine. If it is equals to 0, as we already discussed, if some process is going on and the heat transfer is 0, then we call it as adiabatic process, and the relation between pressure and density will be K rho to the power gamma, that is gamma equals to 1.4. So particles, this one from H1 to H1, it is adiabatic process we are assuming, then N becomes gamma, that is T2 dash T1 dash. This is the particles relation, particle relation of temperature and pressure. So here the N becomes gamma, N equals to gamma. So these two are the important relations, and here N becomes N because we don't know the surroundings property, whether it is what is the N value of the atmosphere, but we just identified since the particle has no heat transfer, so the particle's property N becomes gamma. So this is the surrounding one. Atmosphere. So let's take up these two relations to find out the rho 2 dash by rho 2. Let's go to the next slide. So now we have, what is this? Yeah, T2 dash by T2 equals to P2 dash by P1 whole to the power gamma minus 1 by gamma times, and P1 by P2 whole to the power n minus 1 by n. Remember, this left side is your particle and this right side is your atmosphere, but I removed the notation prime, P2 prime by P21, because we already know P2 prime equals to P2, P1 prime equals to P1. So what will happen if you simplify this? P2 by P1 whole to the power gamma minus n by gamma n. So this is your final relation. So let's couple this with your density. We already know this is equals to T2 dash, this is equals to rho 2 by rho 2 dash, this one, temp T2 dash by T2 equals to rho 2 by rho 2 dash, and that means this will be equals to, if you rearrange it, your rho 2 dash, we need rho 2 dash by rho 2, so that is equals to P1 by P2 whole to the power gamma minus n by gamma n. This is your required equation for your understanding of this, whether it's stable particle or unstable particle or a neutral particle. If you are going from surface, Earth surface to the high above the Earth surface, always P2, that is at H2 height, upper height, if H2 is greater than H1, then P2 is always less than P1. As you go high, your pressure decreases, so that higher atmosphere pressure is less than the lower height atmosphere, that is P2 is less than P1. So it is very clear, if P2 is less than P1, this value is greater than 1. P1 by P2 is, that is P1 by P2 is greater than 1. And the question, it is also given that we have that in the troposphere. Let me, I will show you the question once. Yeah, in the question, if you see, where n equals to 1.235 and n equals to 1 for troposphere and stratosphere respectively. So your n value is 1.235 and 1.4. Okay, so even if you substitute n equals to n equals to 1.235 and n equals to, what is it, n equals to 1, if you substitute, n value is less than gamma. which is gamma equals to 1.4. Your troposphere n value is this 1.235, and sorry, this is for the stratosphere, and this is for the troposphere, and this is for stratosphere. For both the values are less than 1.4. So that means gamma minus n is positive, that is greater than 1, gamma minus 1, where gamma equals to 1.4, n can be between 1.235 to 1. So that is positive 1. Now we got some information that this value is positive value greater than 1, and this value is a positive value that is also not in negative 1. So this means what is telling is rho 2 dash is greater than rho 1. Is it a rho 2 dash? Yeah, so this is not rho 2, this is rho 1, this is rho 2. That is rho 2 dash is greater than rho 2. That means your particle has a density of rho 2 dash. It is greater than the surrounding density. This is the surrounding density rho 2. Since it is greater density, it will always comes down because it is in a less density atmosphere. That means the solution, the answer for this question is it is a stable particle. That means it will return to its original position. Okay, so that's how we need to tackle this question. So it's a lengthier process. I hope you understand. But if you miss somewhere any to understand this question, you can ask the doubts. Okay, if no question, we can proceed further. So this ends our 9th question. Let's go for the 10th question. So 10th question is also connected to the your question number 9. So there the details is not given regarding the pressure, temperature or anything, but here we have some details, and the understanding is also important of the same question. Now let's see the question details. At the sea level, pressure and temperature are 10050 Newton per meter square, and the temperature is 20 degrees Celsius, and unknown altitude. The altitude is unknown, you should remember that. And there the pressure is 7810 Newton per meter square, and the temperature is minus 10 degrees Celsius. Okay. Now the atmosphere between those altitudes is dash and dash meters. That means he is asking, if you see the options, the atmosphere between those altitudes is whether it is stable, unstable, stable, neutral, stable or unstable. We just seen what is stable, unstable, everything, and what is the altitude also, how much is the altitude between these 2 points. And the still question is incomplete. At which the second pair of readings were taken, assuming a linear variation. Yeah, there we have also information that temperature is varying linearly with height, and some more information of acceleration due to gravity and value r. So let's use our linearly varying temperature gradient equations. We already derived in this week 1 from the lectures, you already know, and also explained the brief formulas of these things in the past class. So let's see what is the relation for that. You have pressure. Suppose if you have a temperature at P1, pressure at P1 at low height H1, and you have a pressure at P2 at height H2, and their temperature is T2, and here temperature is T1, and the temperature is varying linearly with height, then P1 by P2 equals to T1 by T2 whole to the power G by LR, where L is equals to a lapse rate. If you see, the lapse rate is your temperature is decreasing with height, that is 20 and minus 10 degrees. So you should remember that your lapse rate is negative. Okay, so let's substitute our values what we have. We can proceed with the substituting, and we can simplify for the unknowns. This is P2, and temperature there at second height is this one, and you need to convert. This relation is valid for the kelvins in temperature, so you have to convert to the kelvins. 0.15 plus 20 by 273.15 minus 10 whole to the power G over LR. So if you simplify this, you will get 1.40 equals to 1.11 power G over LR. So use the logarithmic relations, and to simplify for this L value, you will get G by LR equals to 3.32. This is a simple logarithmic format that you can simplify, and then once you get G by LR equals to 3.22, you will substitute that G equals to 9.81 meters per second square, and given that it's already given in the question that R equals to 287.14 joules per kg Kelvin. Units are very important that you should carefully substitute. So these units are all in same order. So if you substitute and simplify, you will get lapse rate L equals to 10.60 Kelvin per kilometer cube. Note that this is a decreasing kind of temperature, so L should be negative. Okay. Then our question is not to find out the lapse rate. Our question is to find out whether the atmosphere is stable or unstable or neutrally stable. So for the stable or unstable or neutrally stable, we need to, as similar to the previous question, we need to find out that it's a N value. And if the N value and gamma value, we already know gamma, what is the last relation? Gamma minus N by gamma N. This is the important relation that we got earlier to define whether the atmosphere is stable or not. We can also simplify this like this. I will show you how to simplify it. Let me take the eraser. Yeah. Suppose your relation is T2 by T1 equals to, from a previous question, we already derived it how it came, P2 by P1 N minus 1 by N. This is your relation, and you also have T2 by T1 from this. If you take from this, T2 by T1 is equals to P2 by P1 power LR by G. Compare these two. This is the equation 1. This is equation 2. If you can compare these two equations, you will get N minus 1 over N is equals to LR over G. Fine. So let's simplify for the N. N you will get as 1 minus 1 over N equals to LR by G. Then 1 minus LR by G equals to 1 by N. Then G minus LR by G equals to 1 by N. That will give you L equals to G over G minus LR. Okay. Then just substitute your L value as it is. You will get, if you substitute your L value, let me substitute that we have what we got, the L equals to 10.60 and G equals to 9.81. 9.81 minus L equals to, substitute in the modulus form, 9.60 and R equals to 287.14. If you substitute that, you will get N equals to 1.41 and round off, I can say 1.41. But our gamma equals to 1.4 for adiabatic process, no heat transfer. Similar to the previous question, if you compare this polynomial index, how it will get gamma minus N by gamma N. Still our N value, this is our N value here in this question. N value is 1.41, which is greater than gamma. That is, N is greater than gamma. You have to substitute in this, that we seen already in the previous question, that is N is greater than gamma. So n is greater than gamma, what is our understanding from the previous question? That means it is very unstable kind of atmosphere, because this value gives you a negative value. That means the particle will go up continuously. So this is the unstable kind of environment. So we got the question, it is either unstable. There are two options, unstable, unstable. Further is what we need to identify is whether what is the height of this. To find out the height, what we need to do, we just need to substitute in the temperature difference problem. Altitude, because altitude is varying linearly, and you have the L value. L can be written as T2 minus T1 by H2 minus H1. He just asked only the between those altitudes, that is the height, H2 minus H2, that is delta H. You have 10.60 Kelvin per kilometer. So make it by 1000, and this is your delta H, and your temperature difference is 20 minus 10, that is temperature difference is 30 degrees. Difference can be written whether it is Kelvin or Celsius, difference is difference, that doesn't matter. That will give you delta H equals to 2830.20 meters. This is your delta H. Okay. So answer is first one. This is your answer. So that comes to end of our last week questions. If you have any doubts up to this session, we can clear up. We will go to the next session, that last week course content, a small recap, and we will go for solving some problems. Any questions so far? I will quickly show you the slides. Next. These are all the questions. I will quickly go through all these slides. If you have any questions, let me know. All these questions are also uploaded in the NPTEL Excel Google form, that you can download from, or you can view from the link specified there. You can find those live sessions in the your course in the link of that course. Okay. Yes. Question number 10. Okay. Yes, Ashwin.
Sir, one point here.
Yes.
In the videos that you have uploaded, right, the previous recorded session, whatever you were writing on the whiteboard, it was not visible.
Yes, Ashwin. I actually used earlier that Microsoft presentation. In that Microsoft presentation in Teams itself, in that it couldn't record the write-up what I wrote, but people attended that lecture were able to see the details what I was writing, but it was not recorded. That's the problem. I did not test it before. So later I understood, and I uploaded from the second lecture onwards. I started using this complete screen share, and now it is second lecture onwards, it is okay. And the solutions I uploaded, as I commented there also in the first video. Though the video is just showing the words, you can audible, or else you can get the solutions from the comment, a link I shared there in the video bottom. Or also you can find in the session the details, I mean complete links of information of that week material.
Okay, okay, sir.
Except that first video, that remaining all videos will be clear. Sure. Okay.
Okay, sir, I'll go through that.
Okay.
Thanks.
Okay. So let's start our next session. That is, let me open the presentation. Okay. So now we are in the week 3 content. I will give you the overcap of the last week content, so it will be helpful for your understanding to solve all the problems. I will just give you the basic information and important equations. So let's start the content today without any delay. So last week we in the lecture professor covered some important concepts of say Lagrangian and Eulerian form. Eulerian and Lagrangian approaches of fluid flow study. It is like if you are focusing on fixed control volume and you are focusing on the properties what are changing in the fixed control volume, then it is called Eulerian kind of approach. I'm not worrying about what is coming, and I'm not worrying about completely a particle that is here and where it is going and how it is going. I'm not worrying about where it is coming and where it is going. I'm worrying only what is happening to that particle when it comes to this surroundings, whatever the boundary I given, and what is happening to the particle, what is the velocity it acquiring, what is the properties that is creating the change at this particular point. Then that approach, that kind of approach is called Eulerian approach. And if you are following a particle and identifying its properties along its path or along its time, then that approach is called Lagrangian approach. Okay. And generally the velocity field is a key parameter that we mostly work on in the fluids, that we can represent as u. V bar equals to, that is the velocity. U is a function of x comma y comma z comma t, that is u velocity, plus v also, that is a v component of the velocity, that is also a function of x, y, z and t, and w, this is also a function of x, y, z and t. Okay, so now we understood that this is a velocity vector that we have, right? And the approaches, some common approaches that we already seen are control volume approach, control volume, or integral form of approaches. Like you fix a space, something like that, whether it is fixed or movable, you fix some kind of finite space in the atmosphere or in the surroundings, in the environment, that you fix. If I identify some control volume or control space, then this a kind of approach and deriving equations based upon this kind of format is called a control volume kind of approach, or integral form of approach. Another one approach we have is infinitesimal length or infinitesimal system. Infinitesimal system, or this is a differential format, differential form of governing equations you will get with this. You will consider very small amount of fluid particle, that is parallelopoid or whatever it is, very small amount of tiny fluid particle. And then the third one is experimental one, experimental analysis or dimensional analysis approach. This is what we call the dimensional analysis. These are the three basic approaches in the fluid mechanics or aerodynamics, whatever it is, that we follow for understanding the fluids. So in the next, we already in the lecture what the covering topics are the streamlines. The streamlines, from the definition of the streamline, the tangent at any point on a streamline should represent the velocity vector at that point. That means the streamline has a strip, a small element ds bar. If you consider on the streamline, the velocity vector should be parallel to it. That means if two vectors are parallel, its cross product should be equals to 0. That is the definition of the streamline. And then path line, you have to trace a particle from its xyz location at time t0. You have to trace it, you have to find the locus of it as it going with time on the space. That means it is a purely Lagrangian approach, that is dx by dt equals to u of x comma y comma t. In the same way, dy by dt equals to v, dz by dt equals to, this is the velocity equation, velocity in x direction, velocity in y direction, that is dy by dt, dz by dt. This is simply directly a velocity equation. And then the third one is the streak lines. In this, the streak lines, we have to identify locus of the particles that came through a single point earlier time. Suppose I have an inlet here where all my fluids are coming into the tank. Suppose this is a tank I have, and I have an opening here, and I'm sending my fluid. This is the inlet. My fluid is going inlet through this. Though it is a height, it is filling a void. Suppose if I pointed a particular particle here at time t naught, some other time it will be t22, it will come here, and the time 1 second, that suppose is the first second, and after 10 seconds, this is after 10 seconds. At time 1 equals to t equals to 1, the particle identified here, and after t seconds it went here. In the same way, at the time t equals 2 seconds, I identify another particle at the same spot, and later I identified after at the time t equals to 10 seconds, I identified that particle here. At 3 seconds, the similar way, if you find out the locus of, if you find out the, sorry, if you find out the locus of all those particles that are coming from the same point earlier in the time, then that particular line is called the streak line. That means you have to understand that in the streak line, if you integrating the dx by dt, this is also equation of velocity, the time parameters goes like this: t naught less than or equals to t. Suppose the integral dt you are taking, and the time intervals will go from t to t1, where t naught less than or equals to t less than or equals to t1. That means the lower value varies like this. This t should be t naught to t1. Then we'll get the equation of a streak line. Next, let's go to, I will erase this all. Pointer options. Yeah. Okay, let me go to the next slide. Now let's see what is an angular velocity. Angular velocity omega z equals to half of d theta 1 by dt plus d theta 2 by dt is equals to, that we can written in the velocity formats also. But what is this angular velocity means? If you have a distorted fluid element like this, which was earlier a rectangular one, a purely rectangular one, and later it was distorted like this, whatever the angle changing here, del t2, delta t1, based upon this deformation, we defined that angular velocity omega z equals to, that is in the z direction, that is perpendicular to the plane of writing, that we call as d theta 1 by d2 plus average velocity d theta 2 by d2. We can relate this with the velocity as half dv, that is a v component, sec phi component of the velocity, minus du, that is x component of the velocity. You can relate like this: omega z equals to half dv by dx minus du by dy. If you want to write for omega x and omega y also, that is omega bar equals to omega x I cap plus omega y j cap plus omega z k cap. If you are writing for all three components, omega bar will be equals to half of dou w by, this is omega, dou w by dou y minus dou v by dou z, this is I cap, plus dou u by dou z minus dou w by dou x j cap plus dou v by dou x minus dou u by dou y cap. This is very important equation that one needs to understand and not need to remember, but this is the formulation of cross vector of del cross v. How we can see that del cross v, this is the formulation of del cross v, where the del cross v, if you try to see what is the del cross v bar, I j k, I cap, j cap, k cap, and dou by dou x, dou by dou y, dou by dou z, u v w. This is what if you take the determination of this, that you will get the omega 2 omega, but that's why we have the half here. So half del cross v equals your omega bar. And verticity, this is called, we call as a verticity, another parameter. And verticity equals to twice of your omega. Verticity symbol is this one. So we also call this one as a curl of velocity, curl of v bar. This one, then omega equals to, you will get this verticity. This is the verticity equals to 2 omega bar, already written. Okay, so up to this the details of flow, rotation, everything. Now let's go to the Stokes theorem. Stokes theorem is the one that relates line integral with your surface integral. Suppose if you have a line integral v bar dot ds bar, this can be related to the surface integral or area integrals. I can say this, let me say this is a curve. This is the curve C, and this is your area integral del cross v bar dot ds. This is how you can map the line integral of a closed line integral. If you have a closed line, this is my closed line, this is a closed curve, or we can say this closed curve of velocity times a small length, velocity at this point and a small length, not only velocity, any parameter. So you can relate a line integral, closed line integral with the surface. This is the surface with your del cross, that is a curl like this. This is called a Stokes theorem. Okay, then divergence theorem. Divergence theorem, you can relate the surface with the volume of the body. Like suppose if you have a closed surface, it's more or less looks like this. Suppose if you assume this is a closed surface, it's very difficult to show, and drawing representation. Suppose this is a closed surface, and so like consider a droplet of a fluid. A droplet of a fluid is a kind of closed surface, and it has a volume inside it. Now if I want to integrate velocity parameter around the surface, then I can also change it to the volume of the fluid, that is V, with the Stokes theorem, by finding the divergence of this velocity vector. This is how you can relate the volume and surface, volume integral and surface integral, with the divergence theorem. And the third one is gradient theorem. Gradient theorem, there you are relating a vector v bar with surface to volume. There in the gradient theorem, the same thing you are doing, but you are relating a scalar. This is your scalar, that is del p d. Here you will get a vector from this scalar. This is a scalar, and del p will give you the vector. Here you will get a scalar because you are doing a divergence of the velocity field. Okay, fine. And yeah, circulation. I think we will get now the velocity potential concept also. I forgot the name. Okay, if you are here in the class, that now you will see velocity potential from the circulation. So now let me first define what is this circulation. Circulation, gamma equals to closed curve. This is the formulation of the circulation. if you want to understand the definition of it, you can go through the lectures. And this like you are basically integrating your velocity on a closed curve, the curve with a small parameter, the small length, that is ds. And if you are integrating the clockwise, if you are moving in the clockwise direction, then the symbol is positive. The notation, clockwise direction of movement is positive here, and anti-clockwise is negative here. Okay, for the circulation, this is a standard notation. And now, as we seen previously, like we have the relation between line integral and the volume, surface integral, by taking the curl of it, that is the Stokes theorem. You take the curl of the velocity vector, that you can write as surface integral. So that surface parameter is ds, and you just cancel, we just cancelled out the integration on both sides, then it will give del cross v bar n cap. N cap is the unit normal vector, and this is d gamma by ds. This is another formulation of the circulation. Now here we have del cross v. We already seen del cross v is equals to omega. Sorry, this is a vorticity. Del cross v we already seen as a vorticity. So if there can be flows of different types where your vorticity, or we can say it is rotational, if del cross v is finite, is equal to some constant or some value of the time, then it is a rotational flow. Flow is rotational. If del cross v is equals to 0, then it is irrotational flow. If it is equals to 0, then it is irrotational flow. If then your vorticity is also some finite value, or the dependence of x and y, or the spatial or the time parameters. From our vector identity, there is an important vector identity that if some parameter del cross f bar equals to 0, some any parameter f, del cross f bar equals to 0, then there exists f bar. One can write f bar equals to del pi. That means this is a vector. You can write this vector as a del pi, that is gradient of a, this is scalar. Okay, the gradient of a some scalar. So this is what we call velocity potential, since this potential is related to your velocity, because that is del cross v bar equals to 0. That means v bar can be written as del pi, then pi equals to velocity potential. Someone asked at the starting of the this session. So v bar equals to del pi. Now if I expand my v and pi, what is v? V bar equals to u I cap plus v j cap plus w k cap. This is my v. And del pi I can write as del equals to dou by dou x I cap plus dou by dou y j cap plus dou by dou z, this is k cap, and pi. Just substitute the del into the take it inside, I dou pi by j cap plus j cap dou pi over dou x dou y, and k cap dou pi over dou z. So individually each parameter is equals to dou pi over dou x equals to u, dou pi over dou y equals to v, dou pi over dou z equals to w. That means u equals to dou pi over dou x, v equals to dou pi over dou y, w equals to dou pi over dou z. This is your key relation that you need to substitute. If you have some velocity vector, like the question in the assignment, and you seen in the question 11 of this last week, that you have u velocity parameter, v velocity parameter, w velocity parameter, you need to substitute all those things and you need to integrate to get the pi velocity form. You will get some function of x, some function of y. You have to compare the three equations, then you will get the pi equation. that we will see that the question is there in our today's session. We will see it soon, how to solve for the pi. Okay, so that is the velocity potential format. And next we have strain rate matrix. The strain rate matrix can be written as like this: dou u over dou x, dou u over dou y, dou u over dou z. This is dou v over dou x, dou v over dou y, dou v over dou z. Similarly, dou w over dou x, dou w over dou y, and dou w over dou z. This is your strain matrix. So let's take out the diagonal elements. If you take out the diagonal elements, you can see some interesting equation, that is dou u. This derivation is, I'm not going to tell, but what are the diagonal elements? If you sum up, that will give you del dot v bar, that we called as volumetric strain rate. This is called volumetric strain rate, also called as dilatation of the fluid element. Fine. Okay, so let me go to the next slide. Okay, this is the question sequence. I will clear this if you have no queries. Any queries? Okay, so let me clear this slide. Okay, fine. Now we have one more thing, that is scalar gradient and vector divergence. If you have a scalar field like a pressure P at x comma y comma z comma t, any scalar field like this, and if you want to identify its gradient, you have to find del p as described earlier. Del equals to I dou by dou x plus j cap dou by dou y plus k cap dou by dou z. You just need to substitute the p inside, that is the pressure or whatever the scalar field it is, that we call as a divergence. If you are doing this for a scalar field, that means the divergence of that scalar field. Then del p equals to I cap dou p over dou x plus j cap dou p over dou y plus k cap dou p over dou z. This is your divergence. If you are doing the same thing for a vector, that we called as sorry, I just gave you the wrong interpretation. This is not the divergence, this is the gradient of a scalar field. We find the same thing for a, if the thing is for a scalar field, if you apply this parameter, the del, then it is called gradient. Okay, you are finding the gradient, that means the rate of change at which it is higher, the velocity vector is changing at higher space. Okay, that is the what we call as the gradient. And if you are doing the same thing for a vector, then we call it as a divergence, like del dot. We have to do the dot product, that is del dot, and then v bar I dou by dou x plus I cap j cap dou by dou y plus k cap dou by dou z. We have to do the dot product u I cap plus v j cap plus w k cap. If you do the dot product, you will get dou by dou x of u plus dou by dou y of v plus dou by dou z of w. This is also del dot v bar we call. We just seen what is this del dot v bar, and it is called as a divergence of the velocity field or the vector field if you are doing for the vector. Now let's see a quick go through about this some important conservation equations. I will just erase it. Screen. Erase all income slides. Okay. Let's quickly go through some conservation equations that we've seen already in the lectures. That is, for the mass continuity, net mass flow rate out or in through the surface is equals to change in change in mass rate or rate of mass inside the fluid. If you have a small fluid like this and you vectors the flow is entering out or entering in somewhere like this, whatever the mass flow rate in m dot 1 and mass flow rate out m dot 2, this mass flow rate difference is equals to change in mass inside the fluid. Integral format you can write it as dou by dou t. This is the volume integral that's why you get the three integrations here, rho dv plus this is your surface integral, pointer options, that is, and this is your surface integral rho v bar dot ds bar. This is equals to 0. The derivation you can find from the lectures. This is what we called as continuity equation of integral form. Okay, this is the continuity equation of integral form. Now we simplify it further by deleting the integration and assuming this surface, assuming this surface is fixed control surface, it is not deforming or anything, fixed control surface. If you are assuming it is not deforming, then you will get dou rho by dou t plus del dot rho v bar equals to 0. This is the another form of continuity equation that we very frequently use in aerodynamics, that is continuity equation. Remember that it is valid at any point of the flow field, but the deformation of the surface should not be, there should not be any deformation of the surface. There are some constraints of using these things also that you should keep in mind while using these equations. Now let's go to the momentum conservation. Let's go to the momentum conservation. If you have a momentum conservation, from the basic Newton's principle, Newton theorem said laws of motion, force equals to mass into the acceleration. Acceleration, if you want to expand it, you can expand in different finite ways, but we are not going to expand in direct way. I will just give you the final form of equation of the momentum, which consists of several things. Let me just give you some more idea instead of direct formulation. That is, forces equals to, what are the forces you have? You will have generally body forces in the fluid. I'm talking, if there is any body of fluid, any particle that you consider in the fluid, that will generally have the body forces plus surface forces. These two things you will have, body forces and surface forces. What is the body force? Body force can be the gravity, or if there is any additional force that you are acting, that you also can consider in some parameters, and that generally represent, if it is a body force by all sources, what kind of, whether it can be gravity or any additional supply that you are giving to the force, that you can represent as a density rho times, this is the body force per unit volume, per unit mass, I can say, not unit volume. This is F smaller, that is the body forces. This is how you can represent the body forces over the volume. And then you have surface forces are two types. One is pressure, that is minus PdS, Another one is viscous forces, F viscous. Okay, so these are the body forces and surface forces. Acceleration terms also in the right side is equals to mass into acceleration terms. Like, let us look at some important stress terms. Like this viscous forces is yielding. Viscous forces yields, there's several kinds of stresses are there, that is normal stresses, sigma xx, sigma yy, sigma zz. These are your normal stresses, and also you will have tau xy, tau yz, tau zx. These things, there you have the relation. We can say these are important things, that tau xy is equals to tau yx, as your movements is equals to 0, sum of movements are equals to 0, then we can equal that tau xy equals to tau yx of a fluid particle. Okay, this is proportional to sigma xy, sigma epsilon xy, sorry, epsilon yz, and epsilon zx. Okay, so these are your shear stress parameters. All these are shear stress parameters, on these are normal stress parameters. Viscous stresses, these are all comes under the viscous stresses that we are dealing with. We are not going to the in-depth derivation of it, we are just going the overview of it. And if you have the viscous stresses like this, one can formulate the viscous stresses sigma xx. Viscous normal stresses sigma xx is equals to lambda del dot v bar plus 2 mu dou u over dou x. Okay, the same way in the y direction, lambda del dot v bar plus 2 mu dou v over dou y, and another one is sigma zz, lambda del dot v bar plus 2 mu dou w by dou z. Yes, someone has a question? I'm not able to see that, like.
Oh, sir.
Yeah. Yes, what's your name?
Devi Pratap.
Okay, Devi, any questions?
No, sir.
Okay, fine. So let's proceed. So these are our viscous normal stresses. I should write it as viscous. Devi Pratap, you raise your hand again. Viscous normal stresses, and lambda is equals to bulk viscosity coefficient. Okay, and we have one more important assumption, that's the formulation, that is lambda equals to minus 2/3 mu. Mu is the viscosity coefficient, depends on the fluid, which can generally identify by the experimental results. That is mu equals to, this assumption lambda equals to 2/3 over mu, this we called as Stokes hypothesis. Okay, that is what we call as Stokes hypothesis. So if you substitute all these things, you will get your momentum equation. Let me clear the slide. Okay, let's substitute all these things in the momentum equation in just a simple format without expanding the things. Then you will get F bar equals to the body forces. You have to integrate over entire volume. F bar is the body force per unit volume, per unit mass, and you have pressure forces on the surface. These are pressure forces, and then you have viscous forces. Okay, this is your viscous forces. Then let me write further final form of the momentum equation. The time rate of change of momentum, rho v bar dv inside the volume, plus change of momentum across the surface. rho v bar dot ds times v bar, okay, is equals to the forces, the surface forces P ds bar plus, and the surface forces, so body forces you have to integrate over the volume, rho f bar dv plus viscous forces. This will be called as momentum equation. This is a very important form. Suppose, let me expand this for only in the x direction. Here you can see v bar means v can consist of x, y and z. V bar has x, y and z components. If you want to write only specifically for the x direction, you need to separate the things. We are just separating the integration on all the parameters present inside, and we are writing this form. See, this is Fx, that is body force only in the x direction. This is dou P over dou x, that is pressure gradient only in the x direction. Okay. Plus viscous forces only in the x direction. And dv equals to 0. This inside equation we call Navier-Stokes equation, very important one. And this is only in the x direction. If you write the same thing for the y direction and z direction, you will get all the three equations that also we call as momentum equations and Navier-Stokes equations. Okay, let's go to our final equation in the conservation, that is energy equation. Okay, in this energy equation, we'll have internal energy and kinetic energy. Both are related to the temperature, and these two plays key role in the final formulation. Rate of change of your energy format like this with the time, the energy changing inside the system, or energy that is going from the surfaces of the system. This is the volume integral, this is the surface integral. This is rho small e, this is the small v. Small e is representing your internal energy, v is your velocity, and this is your v bar that is going out. This is the energy representing out, going out of from the surface, is equals to the energy that is changing, or whatever the energy is releasing or heating if you are giving any external energy. And then this is a flow work, we called it as a flow work, P dot V. Due to the movement of fluid, we call it a flow work, or sometimes it's also a parameter representing enthalpy. So now this is your final equation. Here E equals to your internal energy, and V equals to velocity, that you know. Any other unknown parameters, Q dot equals to heat transfer rate. Okay, so now we just seen all three equations. What are these equations? Momentum conservation, mass conservation, and energy conservation. That means you have three equations, that is continuity or mass conservation, and momentum conservation or Navier-Stokes, and third one is energy conservation. Okay, these three equations we have, but we have four unknowns in these three equations. What are those four unknowns? That is pressure, density, velocity, and internal energy E. Okay, how you can solve these 4 unknowns using the 3 equations? By using one more variable we have, that is one more parameter or equation we can say, that's not a variable, thermodynamic state relation. This thermodynamic state relation equals to CV. This is constant heat, ratio of constant heat at a constant volume, the specific ratio of specific heat at the constant volume, and that is CV times temperature. For a calorically perfect gas, the perfect gas equation again is we can also have perfect gas equation is P equals to rho RT. So now the variable is T. Instead of E, you replace this E with T. So P rho VT. These are the 4 variables, and this is your additional equation. 4th equation. So 4 equations, 4 unknowns. So these 3 equations can be solved for your flow field conditions to understand the flow physics. Okay. So this ends our discussion of the content. Recap of the content in the last week. Let's start with some problems for today's session. Yeah. Any doubts so far? Okay.
No,
Yes.
sir.
Okay, fine. Let's go to the next first problem of this today's session. Your first problem is you have a 2-dimensional flow is described in a Lagrangian system. See, this Lagrangian system, the flow field is described because you have a time parameter and it is x. Initial parameters are also there, x0, y0, and you have a time parameter. Even the same way for the y also. So it is a Lagrangian system, take as a variable. Now what they are asking is the equation of the flow field, fluid particle in the flow field will be. So here in this equation, all the options they have given is only consist of x and y. So what you need to do is you have to find out only equation of the particle only in the flow field. Suppose the particle is starting here in the x0 comma y0 and it is going to x comma y. What you need to do, you have to find out the equations without involving the time parameter. So how you will remove the time parameter, so to understand within the to get the equation within the flow field, like I can say based upon only x and y as you've seen in the these 4 equations, by simply solving this 2 equations, as you have y equals to y0 e power kt. Let's say you first refine this and try to substitute this e power kt in x0 equation. That means e power kt is equals to y over y0, right? As your e power kt is y equals to y0, just substitute this into your first equation. That means x equals to x0. This is e power kt, right? y0 over y it will become, because you have a minus here, e power minus kt, and so e power minus kt, if you put y0 by y by y0 becomes y0 by y plus y0 times 1 minus again e power minus 2 kt, so it will become y0 square by y square. So that is your x equation. So we just need to do some algebraic simplification, like just try to simplify algebraically. You will get x y square equals to x0 y0 y plus y0 y square minus y0 square. This is furthermore, if you simplify, you will get like y square y, if you simplify for the polynomial format, x0 minus y times y square minus x0 y0 y plus y0 cube equals to 0. This is your final equation. Okay, now we don't have any time format in our equation, so we can trace the fluid particles if you know the x and initial. Suppose I know the initial positions of a particle x and y0, and I want to identify, like if after the x, suppose x another location, where will be the y point of it. So you can easily identify by this. It's a kind of approach by removing the t. Okay, let's go to the next question. The second question is, which option is correct for the following statements? Let's read the statements. The statement 1, the trajectories of the streamlines, path lines and streak lines are equivalent in unsteady flow. And the statement 2, mass exchange is not possible across the stream tube. Streamlines, streak lines and path lines is saying that these are equivalent in unsteady flow. If you see the formulations of the streamline formulation is like this: ds cross v bar equals to 0. And then path lines formation is like this: dx by dt equals to u, dy by dt equals to v, dz by dt equals to w. Okay, this is the formation of the path lines. Streak lines also more or less this formulation is same, but your time integration parameters will vary. So I will just say this is the path lines and streak lines. If you see, the ds cross v bar does not include any time parameter, but the path lines and streak lines are clearly involving the time parameter. So if there is a flow is of unsteady case, then this is not involving with time and this is involving with time, then it is not possible to say that streak lines, path lines and streak lines are equivalent in unsteady flow. So that means the statement 1 is wrong. Okay, but statement 2, what is statement 2? Mass exchange is not possible across the stream tube. What is stream tube? Suppose if you consider a closed curve in the flow field like this and another closed curve like this, ensure that these closed curves are formed by lines of streamlines like this. Important segments of a stream. Sorry, this is like formed by streamlines. These are all the streamlines. Okay, we have a streamline that we are saying the streamline definition at every point of the streamline, the velocity vector is parallel to it. If the velocity vector is parallel to it, is it possible that some mass to cross this stream tube, because the velocities are parallel to it? If something needs to cross this stream tube surface, the velocity should be perpendicular to it, but the definition of a streamline itself is like the velocity vectors are parallel to it. So mass transfer cannot occur across the stream tube. That means statement 2 is correct. Okay, this is your solution of this problem. So let's go to the next question. This question is asking what is shown by the time-lapse photography of nightlife traffic that is analogous to the fluid movement. Is a nightlight traffic. This photograph you can easily understand like how they took this photograph is, suppose at time t equals to 0 second, there is a particle here, and time t equals to, not particle, a vehicle here or a light or a vehicle, you can say a vehicle with this is vehicles are moving this way. So red color indicates that is a backlight, and front lights, these are vehicles are moving this way. So this is a backlight and this is the front light of the vehicle. So that's why you are seeing yellow lines and red lines here. So at time t equals to 0, whatever the vehicles are seeing here, suppose vehicles are not visible and only lights are visible. So at the time t0, you are visible, we are seeing this particular light at this position, and time t equals to 1 second, you are seeing that light at this position, and time t equals to 2 seconds, you are seeing the same light at this position. Here the photograph is taken in such a way that all these lights at these positions are overlapped on each other. That means here also there is a light, and here also there is a light, here also there is a light. That photographs are all overlapped each other, so that instead of moving the light, instead of you are seeing a moving light, you are seeing a line through this. Okay, very closely they packed. So that means every point you are seeing a light. They are overlapped. So they are asking what kind of analogous it is, more or less it is similar to what kind of line in the flow field, whether it is similar to the streak line, streamline, path line and timeline. Timeline is not our criteria, we are not going to discuss. Streamline, we know it is physically not possible to see in the experimental way. Experimentally, it is difficult to see like a flow visualization. It is very difficult. And the path line you can see, but path line definition is you have to trace the particle. You have to see the particle as it's going. Only one particle you need to see. But here you are seeing some particle. This particle, if it is going from this position, you are seeing this particle, and you are drawing a locus of this particle, which are all coming from this position only. You are not tracing this particle whether it is going like this or like this, or not. You are going that you are just overlapping this image, and next where it is from, it is going, it should come from this point only. So you are taking a overlap of all those particles that is coming from the same point in earlier time. So that is called the streak line in our understanding of fluid analogy. Okay, basically you are not tracing the particle that is coming from here, you are not tracing it, you are combining the things. Okay, let's go to the next question. So here in question 4 we have the velocity field. Velocity field V bar equals to Cx, let me write it, Cx I cap minus Cy j cap. Let me take some water. Okay. So our velocity field is V bar equals to Cx I cap minus Cy j cap, where velocity is given in meters per second and x and y are given in meters. The equation of the streamline in the xy plane will be, what he is asking is equation of a streamline. So from the definition of a streamline, what you have, suppose this is your streamline, and at any point your velocity v bar should be tangential to it. If I want to find out, suppose I will take a small piece, almost a straight line. If I want to find a tangent here, what I will do, I will take dx dy, dy by dx. This will give you a tangent. That means this, if the velocity vector also has the same component, that is dy, in the y direction the velocity component is v, it's a small component v, and in the x direction your velocity vector is u. Okay, that means according to the streamline, from its definition also you can write this, or you can directly write for your simply understanding, because if you understand the meaning of it, streamline, you can directly write this. There's the two tangents, velocity tangent also dv by u, and a line tangent is dy by dx. So let me write it again, v by u equals to dy by dx, and v dx equals to u dy. Just substitute that u and v. We have u equals to cx and v equals to minus cy. So if you substitute it, minus cy dx equals to cx dy. Okay, let's do the variable separable. If you do the variable separable and apply the integration, you will get, cancel out the c on both sides, you will get integral 1 by y dy equals to minus integral 1 by x dx. That is ln of y. You have limits, suppose there is no limits and you can use the constant, is equals to ln of x plus, suppose let's say the constant, whatever the constant that you are getting, that is ln of c1 or ln of c. Let's say that is the constant is c. Since it is a constant, I can write it as a logarithmic format. Okay, so you have a minus here, and this, if you simplify, what you will get is ln of y equals to ln of x, c by x. Then you will have x y equals to constant. This is your equation of streamline. Fine. Okay, let's go to the next question. Okay, in this we have question number 5. and session is recording. Nice. Okay. In this question number 5, he's asking that if a particle is moving in the same flow field given in the question 4, remember that we are dealing the question number 4 data here. Determine the velocity magnitude of a particle at t equals to 5 seconds. If it is located at 1, 4 at t equals to 0 second, assume c equals to 0.35. Given that the velocity field v bar is again, what is the velocity field? Cx I cap minus Cy j cap. Okay, if you have the same velocity field and your initial points are 1, 4 at t equals to 0 and some after time t equals to 5 seconds, you need to identify what is x comma y, and the requirement is velocity magnitude at t equals to 5 seconds. How you can find the velocity at t equals to 5 seconds means, if you know the position of the particle like x and y at t equals to 5 seconds, just substitute those values, like I have some x equals to 5 and y equals to 10, something like that. Substitute those values in the velocity equation here. If you substitute x and y values, you also have the c value, then you will get the velocity at that particular time and position. So this is how you can find out the velocity. But how can you find out? You just need to use the path line format. The path line format is dx by dt equals to u, dy by dt equals to v. Okay. So dx by dt equals to u and dy by dt equals to v. So just substitute your values of u and x. That is dx by dt equals to u equals to cx and dy by dt equals to minus cy. And then rearrange the things. If you rearrange it, let's say 1 by x dx equals to c dt and integrate it. Integration from like x units. X is varying, the initial x naught is 1. So 1 to, I want some final value, that is x, that is I don't know what is that final value, so x. It is varying starting from 1 and going to x. I know the time parameters. Time is starting from 0 and it is going to 5 seconds. In the similar way, you integrate for y also. Y initial location is 4, going to some particular location y after 5 seconds. That is 1 by minus, this is minus 1 by y, and this is dy. You will get integral 0 to 5 c dt. If you substitute all the values and if you solve this integration, you will get ct equals to ln of x by 1 and y minus ct equals to ln of y by 4. This is what you will get. Okay, so once you substitute this, and let's substitute the c values also. You have t value also. T is 5, t equals to 5. Then let's substitute that t equals to 5 and 5 seconds. This is 5 seconds, and c equals to 0.35 seconds. Okay, then you will get what you will get. Just substitute those two equations, that is x equals to e to the power ct. If you simplify this, you will get x equals to e power ct and y equals to 4 e to the power minus ct. Fine. Now just substitute these two in this and you will get x equals to 5.7546 meters and y equals to 0.6951 meters. Now we have the x and y values, but we need to find out the velocity magnitude. To find out the velocity magnitude, we need to do b equals to cx I cap minus cy j cap. At t equals to 5 seconds, what is your x and y? You just need to substitute it, and c equals to, we have 0.35 and x equals to 5.7546 minus 0.35, this is I cap, times y equals to 0.6951. And just substitute this values, you will get v bar. You will get a v actually is in vector format that you need to substitute in like you need to find out its modulus. This is your vector format. I need the modulus of it to find it. How do you can find out the modulus? Root x square plus y square. Your x value is this one and y value is this one. So, or I can say u square plus v square to not confuse you. This is u velocity and this is v velocity. U square plus v square. If you substitute that, you will get modulus of root. Sorry. Yeah. Here you will get 2.0141 square plus of minus 0.2433 square. That will be equals to 2.0287 meters per second. Fine. Okay. Now in this assignment, we are not going to, like, we already seen what is the velocity potential, but I think Devi, you asked for how to solve for the velocity potential equation, right? Are you there?
Sir,
Yes, sir.
Who asked? I don't remember exactly his name.
Tanmay.
Tanmay, sorry.
Yes.
Yes, Tanmay. I will give you the idea of it. I don't have feasibility to tell the entire details, but I will give you one more time. Like, how did you get like any idea? But should I explain again?
I got the idea, sir.
You got the idea. Like how you need to identify. It's already there in the lectures, but for your understanding, I'm just telling V bar equals to, if the flow is irrotational. First, you need to identify. They're asking you to find out the velocity potential, but you need to identify whether del cross V bar equals to 0 or not. If it is not 0, then potential function del pi, this pi does not exist. If it is exist, that means del cross V bar equals to 0. You have to clarify this with your velocity function. Okay, now if it is rotational, assume it is rotational, the potential function exists. Then del pi equals to dou u by dou x, and this is I cap, plus j cap dou v by dou y, plus k cap dou w over dou z. If you compare, because del pi equals to v bar, that is equals to u I cap plus v j cap plus w k cap. That means, so this is pi, sorry, this is not w, this is pi. Then dou pi over dou x equals to your u, dou pi over dou y equals to v, dou pi over dou z equals to w. Let's suppose your flow is two-dimensional. For your easier understanding, there is no w vector. If your flow is two-dimensional, and if you are trying to integrate, and u is some function of x, suppose d pi over dou x equals to f of x, u is some function of x, and d pi over dy, v is some function of y. Okay, then you do the partial integration by integral dou pi equals to integral f of x dou x. In the similar way, you do the partial integration here, integral f of y dou y. What you will get here, you will get pi equals to, since you did the partial integration and your flow is two-dimensional, you will get some suppose after integration you will get the f of x, function of x something, capital F of x, plus some h of y. Okay, h of y, because y h of y, you did the partial integration, there is no y parameters here, some function will come, that is a h of y. In the same way, here you will get pi equals to some capital G of y plus I some m or whatever the function, this is a capital H, I will say capital H of x. Okay, then you compare these two equations. If you compare these two equations, here also you have g of y, here also you have g of y, and here also you have h of x and f of x. So functions are same, are common, and you are comparatively can write one common equation, f of x plus g of y. This is your velocity potential. Clear? You just need to substitute your values instead of doing these variables. I did it in the variable format. You need to use the whatever the respective velocity is given to you. Okay. Any more doubts? Okay. I hope it is clear to you. I will go for the next question. Question number 5. Let's take this question, and two more questions we can take, and then we can wind up for the today's session. That the velocity field in the fluid medium is given by v equals to, this is some lengthier velocity equation, like I don't want to read it, but you can see, simplify that u equals to 3xy square, and v equals to 2xy, and w equals to 2zy plus 3t. Here you have time parameter, so it is unsteady velocity field, and t is the time parameter. He is asking that magnitude of rotational velocity of the fluid element at 2, 4, 3. What we need to find out is magnitude of rotational velocity, that is angular velocity or rotational velocity. We already seen this formulation in the recap of this content. And at a particular time, that is time t equals to 4 seconds, about x, y and z. You're asking the things of all the about x and y and z. Suppose if we want to find out only about the z direction, you need to write it is a half of dou by dou y plus dou by, sorry, this is minus dou x u and v. But if we want to write the same, it is very clear, that is z, y, x, and it is x, you have to use the opposite velocity, that is v. It is y, so we have to use the opposite velocity u. So it is very easier to write for the z. But if we want to write this is the angular velocity equation, a rotational velocity. If you want to write it for all the three-dimensional, how can I write? We know that angular velocity omega for all the three components, it is equals to half of del cross v bar. We already know what is this del cross v bar, that is a divergence, that is half of I cap, j cap, k cap, right? And then dou by dou x, dou by dou y, dou by dou z, and then you have v bar, u, v, w. Let's simplify this, let's expand this. You will get omega equals to omega bar equals to half of dou w by dou y minus dou v by dou z I cap plus half of dou u by dou z minus dou w by dou x j cap plus half dou v by dou x minus dou u over dou y k cap. This is your angular velocity equation omega. What you need to do is you just need to substitute your all the values of w, x and z. We already have u equals to 3xy square, 2xy and 2zy, 3t. If you just substitute and simplify, what you will get, let us substitute this I cap of half of dou by dou y of 2zy plus 3t minus dou by dou z of 2xy plus j cap of half of dou by dou z of 3xy square minus dou by dou z of 2zy plus 3t plus k cap of half dou by dou x of 2xy minus dou by dou y of 3xy square. So this is your complete equation. You need to simplify this. If you simplify this, you will just get z I cap plus y minus 3xy k cap. This is the only small equation that you will get. Once you get it, what you need to do is asking that get the values of the angular velocity. This is your angular velocity now in 3-dimensional, all x, y, z, where z equals to 0. Because you can see I cap only, k cap only remains, remaining k, z cap is becomes 0. So once you get it, you just need to substitute x and y and z values, where x equals to 2, y equals to 4, and z equals to 3. You have t also, t equals to 4, but this angular velocity does not depends on time. That's why there is no time parameter yielded in the final omega result. This is omega bar. Okay, so just substitute these values, 3 I cap plus 4 minus 3 cross 2 cross 4 k cap. You will get 3 I cap minus 20 k cap. This is your omega. So you have 3 units of x and 0 units of j and minus 20 units of k. That is your omega. So we solved it. This is the question solution. We have 3 more minutes. If you have any questions, you can quickly ask. We can take 1 or 2 quick questions. Or people are asking that TS are also replying your questions in the Google Forms. I believe like if you have any specific questions or you want to discuss directly, you note down that question or you take a photo of that. You can present the screen or you can send maybe in the Google Form if possible, or you can write there and you can join. Please join the session. In the starting of the session, you can clear your doubts easily. If I'm going to cover that particular doubt, I will cover that in this session, or else I will answer you at the starting of the session itself. Any doubts so far? Okay. If no doubts, I'm going to end this session today. We can discuss the remaining questions in the next session. Thank you for joining. See you all in the next session. Thank you.
Thank you, sir.
Thank you. Thank you, Ashwin.